So in this question about curve sketching, we're getting a little bit different type of problem. So we've got a gradient function given to us of this curve, and the gradient function is given to us as 3 outside of x minus 1 all squared. So we can see our graph there. It's when x is equal to 0, so x is equal to 1, dy dx is equal to 0. When x is equal to 0, dy dx is equal to 3. So we're given that information from that graph. So first part says we know the stationary point's located at x is equal to 1. Can we justify this statement? Well, as we just said, at x is equal to 1, we know the graph that dy dx is equal to 0. So we know stationary points exist when the first derivative is equal to 0. So that must indicate some sort of stationary point. There we go. Second part says comment on the sign of dy dx for all x except that x is equal to 1. So we just worked out that always there was 0 there. But if we look at the rest of the dy dx values, they're all above the x-axis, which means they must always be positive. So what can this say about a curve, about the curve of the function of x? Well, the curve must always be rising except when x is equal to 1, because we know it's stationary at x is equal to 1, but the gradients otherwise of the curve must be rising. So here's the graph of the second derivative there. So we can see that the second derivative at 1 is equal to 0. And in completing this table, we know that the sign of the second derivative, well, before when x is equal to 0, well, we get minus 6, so it must be a negative value there. And after, the sign of the second derivative must be positive, because at 2, and all the values greater than 1, there it must be positive. So what's the nature of that stationary point there? Well, see, we've got a stationary point at 1, but also a changing concavity, because the gradient 0. Sorry, the concavity at 1 is 0, but it changes from concave down to concave up. It must be a point of inflection as well, so it's a horizontal point of inflection. And that makes sense because the curve rises, stops, and then rises again from our first derivative. So that would tell us that has to be a horizontal point of inflection as well. So we didn't see the function at all. We didn't have to graph the function at all, but we've been able to determine a lot of information about that just by giving graphs of the first derivative and the second derivative. So if we consider this function here in question 6, dy dx, x squared 2x minus 1, x minus 1. What's the nature of the stationary point at x is equal to 0? So, okay, we know that we're going to get a stationary point at x is equal to 0. So how do we determine the nature? Well, we test either side of it. Instead of getting the second derivative, this would to get the second derivative, we'd have to expand this and then derive it and then test our value of x is equal to 0. That's not easy. Let's just put some values in. So if we put minus 1 in, put minus 1 in there, minus 1 in there, minus 1 in there, we look and we get a positive gradient. If we put a quarter in there, and notice I'm going to use a quarter. I'm not going to use 1. I'm not even going to use the half, because it says it's got a stationary point at x is equal to 0, but that would give me a stationary point at a half. That would give me a stationary point at 1. So that's why I'm using 0.25, so a quarter to sub in. So just be careful. People have already asked about how far to go, but it just depends on our stationary points. Well, stationary points would exist at a half and 1 there. So that's why we've picked a quarter, if you're wondering why is that the case. And sub the quarter in, we see it's positive as well. So we know when we've got a positive gradient, 0, then another positive gradient, that we have a horizontal point of inflection. The curve rises, stops, and then rises again. It's a horizontal point of inflection. So there we go. There's a couple of different type of questions, but again, calling into play the ideas about the first derivative or the second derivative, to be able to determine the nature of the curve and be able to graph it or describe something about the curve without actually drawing it up.